markets that we serve, we actually split our business into two separate verticals. One is the life sciences, which is mostly on the pharmaceutical products and medical devices, and the other being the industrial and environmental, which is the one that I support. Our history actually has been pretty long, and we've gone through a number of transitions, as you can see over the years. That we started out originally back in 1992 as the Sievers brand, but we have been acquired by multiple companies over the years, and as present, we are part of the Veolia Water Technologies and Solutions Group. Okay, but nevertheless, the Sievers line of products are still very much relevant to our customers today. Our mission, just again very briefly to share with you, is basically to create differentiated and innovative technologies for analytical solutions that will enable our customers to better manage and conserve one of our most precious resource, which is water. So without further ado, let me dive into the key topic. Why do we want to monitor organics, right? So I'll try to break it down into maybe three different perspectives. One is on the regulatory, one is on process optimization, and the last is on quality control. So monitoring organics in a water sample is very important for regulatory purposes, mainly about drinking water as well as for wastewater. So for drinking water, of course, it's pretty important that the water that we consume is of a certain level of cleanliness, that we don't have organic contamination in the water. So drinking water treatment, organics monitoring is definitely a key part of that. Similarly, for wastewater, when we discharge wastewater back to the environment, we don't want to cause any detrimental impact on the environment by having too much nutrient in the water, and organics is definitely a key part of that as well. So any effluent that we discharge back to the environment, organics monitoring is necessary to ensure that the water that we discharge is safe for discharge and it doesn't cause any impact on the ecosystem. In terms of the optimization, well, we do have a number of customers who monitor organics to improve their process. It can be in the treatment, it can be to protect certain critical assets, such as their heat exchangers, their boilers, their RO membranes. So optimization is definitely a very strong motivation for our customers to understand the water quality as it flows through their process. And the last part on the quality control. So some of the water that we use in our manufacturing, they have to be of a certain level of cleanliness in order to make the safe product and high quality product. So what are the examples? If you're making a medical device or pharmaceutical drug, you need to have a water that is safe for consumption, right? Likewise, when you talk about manufacturing electronic components, if some organic contamination is present in the water, then it may cause a short circuit in the electronic component and you will fail. So for robustness purposes, quality control of the water is very important. So regardless of which perspective I'm talking about, at the end of the day, the idea is the same. We're trying to make sure that the water is fit for purpose. And if you don't have information about the water quality, then there's no way you can make an informed decision, whether in how you want to manage the water, whether you should use it for the process, whether you should go for additional treatment, or whether you should send it to waste management. You do need that information. So analytics is very important, and organics monitoring is certainly a key part of that. And again, why we want to focus on organics in this presentation is because when we talk about a water sample, of course, we have two types of organics that are, two types of contaminants that are present. We have both the inorganics as well as the organics. But as my illustration is trying to show here, the organics contaminants are actually a much bigger presence in the water sample, and it dwarfs the inorganics by a large amount, right? So inorganics, we're talking about things like metals, minerals, and salts. But in terms of the organics, there's actually quite a number of organics that we use in our processes, and eventually these compounds do find their way into the water system, whether it's in the waste or is in the source water that you are taking from, let's say, a river or from the sea to use in your process. So you're talking about things like dyes, solvents, proteins, hydrocarbon. All of these compounds are actually carbon backbone, which means they are organic in nature. So certainly, if you want to understand the breakdown of the contaminants in your water, organics is a major one that you need to pay attention to. So coming back to monitoring organics in the water, why is it so important? Again, I want to take it from the application point of view. First, by looking at utility water. So when I talk about utility water here, I'm referring to things like the boiler feed water, the steam and steam condensate. These are very common utilities that almost every plant will have, right? So in many plants with many of our customers, these utilities are often recycled for water savings and also for process efficiency, because things like your steam and steam condensate, they contain a lot of thermal energy that can be transferred and recycled to another stream, again, to save on the cost. So the thing about recycling these streams is that your water system will now operate in a closed loop, right? So utilities are operating in a closed loop. And in this closed loop, you have a number of different equipment. You have your resin beds, you have membranes, you have maybe cartridge filters. At the same time, you have heat exchangers, you have cooling towers. All of these unit operations actually are opportunities for contamination to occur, something to get into the water. So for example, if you're looking at a heat exchanger in this, like I'm showing in this diagram here, you might have your steam coming in on the orange side and then going out as condensate, hot condensate. And on the shell side, you're trying to heat up a secondary fluid. This secondary fluid could be something like a coolant, like ethylene glycol, or it could be perhaps a diesel fuel that you are going to heat up to send to the burners. So this exchanger, of course, we want to allow thermal energy to transfer without actual physical mixing of the fluids. But over time, we know that sometimes leaks can occur, right? And then once they develop in the heat exchanger, then you have physical mixing. That means whatever condensate is coming out from a heat exchanger can be contaminated by either the coolant or by the diesel fuel. So if you send this condensate back and use it as, say, makeup water for your boiler, then what you're doing is you're actually sending contaminants into your boiler. You're causing problems that will eventually surface as either corrosion or maybe deposition inside the boiler. So when we talk about utilities, it is a very common customer practice, to monitor the quality of the utilities by looking at just two parameters. One is pH and the other is conductivity. Now, all these are good parameters, don't get me wrong. But when it comes to trying to detect the presence of an organic contamination, for example, ethylene glycol or diesel fuel, none of these maybe will affect the pH and conductivity, because these organic contaminants, they tend to be uncharged and they tend to be pH neutral, right? So if you're just looking at pH and conductivity data alone, you may not be able to see this contamination happening, in which case, then the process engineers may will end up having poor visibility of their process, and then they will end up making incorrect process decisions. Like I said here, if you're sending the contaminated condensate for boiler makeup, basically you are setting up your boiler for problems in the near future. We've experienced, actually, seen some of these organic contaminants, such as halogenated or heteroatom organics, which I'm trying to show here. It's a carbon backbone that is bounded together with an inorganic compound such as chlorine, bromine, nitrogen, sulfur, and phosphorus. By themselves, they are pretty harmless, right? But the thing is, once these contaminants get into your water system, and perhaps if you send them to an area or in your process where there's high temperature or high pressure, then there's a chance that these organic compounds can react, right? Once they break down because of the temperature and pressure, then they start to release certain harmful compounds back into the water, such as your chlorine, your bromine, nitrogen. And when these compounds are released, then they will basically cause corrosion or cause deposits inside, not necessarily only the boiler, but everywhere throughout the water system. So we do have one example. This is from some time ago, but it's still very relevant today. The example that I'm sharing here is from a nuclear power plant in Canada. And so this happened way back in 1999. And what they do was they use a anion exchange resin for their treating their water before it goes into the boiler. So this is a very common practice. Once the resin is exhausted or saturated, then they will put in a fresh batch of resin and rinse it down before they put back the bed online. But in this particular instance, they replaced the resin with a batch that was defective. So this defective batch actually was releasing chlorinated organics without them knowing. So simply by monitoring the, in this case, the conductivity, they think that, oh, my resin has rinsed down sufficiently. I'm going to send it back to, I'll put it back online and send the water into the boiler. But what happened was these chlorinated organics actually did not rinse down completely, right? So the organics level was still high. And when they put the bed back online, the chlorinated organics actually got into the boiler and it broke down, and suddenly the chloride levels in their boiler system spiked. It spiked so high such that it forced them to perform unscheduled blowdown. So you can imagine the severe disruption that this caused to the customer, in terms of the productivity and the lost time. Not to mention the amount of water that they subsequently need to flush out the whole system and top up the boiler again. There is also another perspective of looking at the importance of monitoring organics, which is from the wastewater point of view. And here, I think we've talked about this earlier on, why we need to monitor organics in wastewater is for regulatory compliance, to make sure that we don't cause any impact onto the ecosystem. Even within the wastewater treatment process itself, before getting to the effluent discharge, sometimes it's also very helpful for customers to monitor organics. We do see benefits of monitoring the organics even at the very start of the wastewater treatment process, where the raw wastewater comes in, because then you understand your wastewater organics loading. You know how much of chemicals that you need to dose, so you can actually have a tailored approach to your chemical dosing. Likewise, if you have a biological treatment or aeration tank in your wastewater treatment process, then organics monitoring actually helps the customer to balance their so-called food to biomass ratio in order to maintain a very healthy aeration system and to minimize the sludge formation. I also want to take some time to talk about the so-called current state of affairs when it comes to wastewater monitoring. The two parameters that we'll commonly encounter, or the customers will typically use to so-called track the organics in the wastewater, is BOD and COD. So BOD stands for biochemical or biological oxygen demand, and COD is for chemical oxygen demand. I believe most of our attendees on the line are very familiar with these two parameters. But I just want to take some time to talk about how they actually can affect, of course, inaccurate readings. So starting first with BOD, if you consider the test is trying to look at how much oxygen is required for the microbial to break down or contaminants in the water. The test itself takes a very long time. Most of the time, we're talking about BOD5, which means that they need to incubate the sample for 5 days. And because we are looking at microbial action can vary a lot depending on what's in the water, right? So if you have some microbial inhibitors, or sometimes even you have some things that promote microbial activity, it can cause a very big variation in your BOD results. Plus again, if you look at the time taken to get a single data point, is 5 days, right? In terms of process control, this isn't necessarily the best tool to use, because at the end of 5 days, perhaps your water quality has already changed. So relying on BOD to make a process decision is not very efficient. Nevertheless, I know this has been a legacy parameter that's been around for a long time, and many of the country's regulations are probably still written around BOD, even COD. COD, on the other hand, is a little bit better because now we are looking at the so-called the oxygen required for chemicals to break down the organic contaminants in the water. So we are typically adding a very strong oxidizing agent like permanganate or persulfate sometimes, or dichromate. So the thing about these chemical oxidizing agents is that they are not specific. In fact, they will oxidize everything in the water that can be oxidized. So not necessarily just organics, but if you have other compounds like nitrates, nitrites, sulfites, even some of the iron F2 can be oxidized to F3, and that will be actually so-called accounted for in the COD number as well. So COD is helpful, but it doesn't necessarily limit itself to just organic. So take note of that. In terms of the time taken to get a single data point, normally when you get the sample and you start the test immediately, it will take 2 to 3 hours, right? So even that is not exactly real time, especially for a process where you might have more variation in the water quality. And the last thing that I want to add about this COD is that there are a number of countries who are in the process of phasing out COD because it uses a hazardous chemical, the dichromate, and also mercury. So these so-called byproducts or waste products are extremely difficult to handle, and therefore this test is actually being phased out in a number of countries. One last parameter to talk about, which is UV, because when you talk about wastewater, they actually I've seen a number of customers who do rely on a UV probe or spectral photometer to so-called monitor for organics in the wastewater. Now UV absorption, we know that it is good for only a certain type of or certain class of organics, and it's only good for maybe the wastewater samples that are relatively clear. But if you talk about samples that have a little bit of turbidity or color even, then we know that interference definitely occurs. And at the same time, you can see from this table here that if you have compounds like ferrous iron, nitrite, nitrates, chlorates, chlorides, ozone, these are actually very common compounds which you can find even in the treated effluent. So these are known to cause interference with the UV probes, and therefore, from my point of view, UV is not necessarily the most accurate way of monitoring for organics in the wastewater. At the same time, it is in a way also a surrogate measurement, because you're looking at the absorbance of the UV rather than trying to actually analyze for the organics. So I think this sets the stage for the next section of my presentation. Why should we use TOC for organics monitoring? So TOC, as I talked about at the earlier part of my presentation, stands for total organic carbon. it measures all the organic carbon in the water. So anything that's of a hydrogen carbon backbone, it can be oxidized, and the end product of that oxidation is carbon dioxide, which we can very selectively measure in our TOC analyzer. So unlike like a COD test, which also uses a chemical reagent to oxidize the sample, here we are being very, very specific to just organics, right? So this diagram, I hope it can very quickly give you an idea of the carbon present in the sample and how we classify it. So if you consider the total carbon in the sample, we typically break it down into two groups: the inorganic carbon as well as the organic carbon. So inorganic carbon, short IC, is essentially just dissolved carbon dioxide, right? It's dissolved carbon dioxide. When it dissolves in water, it will equilibrate depending on the temperature as well as the pH, and it can possibly exist in different forms, such as the carbonate and the bicarbonate. So it might ionize, right? That's relatively easy to understand. In terms of the organics, however, we can again further break down into two more groups. One is what we call the purgeable, and the other group is the non-purgeable. So not to confuse the audience, but basically the difference between these two are the volatility of the organics. So the some organics of the maybe the lower molecular weight very easily it can vaporize or evaporate into the atmosphere. So once we introduce a gas, any inert gas like N2, for example, to purge the sample, then these organics are very easily so-called vaporized and lost to the atmosphere. So these are the group which we call POC, or purgeable organics. You can think of it as volatile organics as well, VOC. And then the organics that do not evaporate are then called the MPOC, right? So MPOC here, again broken down into two more groups, either the colloidal and the particulates, and also the dissolved, right? So for some specific applications, customers do want to measure just the dissolved organics alone. So this is relatively easy because all they need to do is to take the water sample, run it through a filter paper, and then measure the filtrate. Okay, so why do I want to advocate TOC analysis for monitoring organics? Is typically TOC analysis can be completed very quickly, right? It's very fast, less than 15 minutes. Usually you get one data point. So from a process control point of view, having online TOC can even allow the process engineer to make so-called real-time or immediate decisions on how they want to manage their water. The analysis itself is easy. There's no complex sample preparation required. In rare cases, we may need to do dilution, but that's about it, right? You don't really need to have other reagents that are so-called added, and you need to titrate or do any digestion steps even, right? TOC analysis itself, because of the way that we single out just the carbon dioxide from the organics, it becomes very accurate, right? The TOC analysis looks at only the organics because we are looking at just the carbon dioxide that comes from the oxidation of organics. We don't bother about the other so-called the chemical species that are present in the water sample. So just to be clear about the message that I want to share with the audience is that I'm not saying that these parameters like pH and conductivity and TDS are no good. They are good, but they are meant for their own purpose. So for example, if you're looking at inorganic contamination, then conductivity and TDS is probably a great way to go. But if you're trying to monitor for organic contamination in your water sample, then it is much better to use a tool like TOC. And so TOC in a way completes the picture and you get a much higher process visibility to reduce any risk of how you manage your process. So coming back again to my earlier approach, when talking about using organics for utility water, here I do have some examples of guidelines from both ESME as well as the European standard on how they actually give recommendations for TOC values in the water for that is to be used in the boiler. So for ESME, this is broken down based on the operating pressure of the boiler. So those boilers, especially the newer ones which operate at much higher pressures, there is an increasing pressure for them to actually operate at very low TOC levels. Most of the customers that I visited who are just setting up their boiler systems, they actually have TOC levels at 100 ppb and below. Right. Similarly, for European standard, they do have certain requiremements for both the boiler feed water as well as the main water. This one is talking about wastewater. So from the wastewater point of view, I want to share a case study to show you why TOC is a much better parameter to use for wastewater monitoring as compared to either COD or even BOD. So this particular customer actually had a plant expansion, and you can see this is their wastewater treatment process, the wastewater treatment train up here. So their equalization tank was a little bit undersized because of the plant expansion. And previously, they are basically managing their wastewater by monitoring the COD on a daily basis. But they were getting a lot of upsets in their aeration tank. So they did not know why, because based on the measured COD, they found that actually the data is very stable. So over here on this graph, if you're looking at the red circles, those are the COD measurement points that they were getting on a daily basis. So we went in and actually did a demonstration at this customer by hooking up our online TOC analyzer. And because the TOC analyzer is able to complete the analysis in a much shorter time, so we in the same period of time, we are able to get much more data. So there's higher data resolution, right? And we actually able to do a correlation study at the same time, between the TOC value and the COD value. So when we took the TOC values that we were able to obtain, and we did the correlations and plotted it on the same graph, we were able to see that there were actually these fluctuation, these spikes that was happening so quickly that when the customer was taking their daily COD samples, they were not able to capture these spikes. So the spikes are the ones that are actually getting transmitted down to their aeration tank and causing a lot of these disruptions to and upsets to their aeration tank. So once they had this data, they were able to have much better control over how the water from the equalization tank was released into their bioreactor, and therefore they could subsequently stabilize their process. So coming to the so-called last section of my presentation, I just want to very quickly introduce some of the solutions that Sievers can offer for organics monitoring. So the first up is our M9 TOC analyzer. As you can see here, we actually have 3 different models available. We have a portable configuration on the left, followed by an online configuration at the back. And in the front right here, we have the lab model, which is can be coupled together with this auto sampler, right? We have very good accuracy on this model, down to 0.03 ppb, and the upper limit is 50 ppm. The measurement cycle is just 2 minutes. So 2 minutes is all it takes to get a single data point for your water sample, right? For certain options that can be added on to the analyzer. We actually can tolerate water temperature up to 90 degrees Celsius. So it's actually very suitable for measuring like even the hot condensate. There's no need for the sample to be cooled down first before we measure. There is no carrier gas requirement. For some of you who might be familiar with TOC analyzers, some of the TOC analyzers that you use may require either nitrogen or CO2 free air to operate. So for this one, it's actually very easy to operate and to use. Even the calibration, you only need to do it once every year and can be done on site. The unique technology behind the M9 is really about the detection. So we have this, what we call the membrane conductometric detection technology. So this is a patented technology from Sievers. Let me pause the animation for a moment. So just to very quickly explain what this is all about is when we have the sample get into the analyzer, we have to oxidize it first into carbon dioxide. So this is happening at the top at the UV reactor, right? So once the sample is oxidized, it gets into this CO2 transfer module. And over in this module, we have a gas permeable membrane that selects for just carbon dioxide. Only carbon dioxide is able to diffuse across this membrane over to the right side. The right side is where we have the measurement loop, right? So nothing else is able to cross. So again, what I'm trying to show here is that we are very selective about just carbon dioxide that is coming from the oxidized organics. So when this carbon dioxide comes over to the measurement loop, it will ionize into the carbonate and bicarbonate form, and it will cause a change in the conductivity of this water here in the measurement loop. So subsequently, when we measure the conductivity of the water, we are very accurately able to determine how much carbon dioxide was there in the first place, right? This is a so-called a self-sustaining loop inside the analyzer, because once the measurement is complete, the water will go through a CO2 removal, is a scrubber, so that it's regenerated for the next measurement step. This is in contrast with the technology that some of our competitors use. So our competitors may use what we call a direct method of measurement, where pardon me, yeah, right after the sample is oxidized, they will actually measure the conductivity immediately without selecting just for carbon dioxide. So they're assuming that everything inside the sample which contributes to conductivity is carbon dioxide, which may not be true, because there can be other things in the sample like sulfates and chlorides that can also contribute to conductivity. So in that sense, their reading is significantly less accurate compared to the Sievers instrument. And then the other product that I want to introduce here is the Sievers Innovox TOC analyzer. This one is available in two different configurations. On the top, we have the lab model, again coupled with the auto sampler, and the bottom we have the online model. So this is meant for so-called the more dirty applications, for example, wastewater, because it can measure all the way up to 50,000 ppm. It uses, again, a very differentiated measurement technology called the supercritical water oxidation technology. So this technology allows the analyzer to handle samples that have a lot of particulates, that have a lot of dissolved salts, like chlorides inside, high chloride samples. High chloride samples typically will cause interference to the TOC analyzer, but with the Innovox technology, it can be easily overcome. So again, very quick explanation about the supercritical water oxidation technology is that once the sample gets into this analyzer, we're actually heating it up to 375 degrees Celsius within a confined reactor tube. So it will pressurize up to 220 bars. And under this combination of temperature and pressure, we are forcing the sample into this supercritical condition. So supercritical condition means that the water is not exactly in the liquid phase or in the gas phase, but right at the boundary. So it has actually the properties of both liquid and gas at the same time. Now, why do we want to do this is because at a supercritical condition, we have organics dissolve very easily in the water, which means that it's easy to oxidize these organics. But when it is in supercritical condition, inorganic salts become insoluble in the water. So your chlorides, sulfates, all these actually, they will precipitate out of the sample when it is in a supercritical condition. So they don't get to interfere with the reaction anymore. So we create this very good so-called condition or environment for the oxidation of organics to take place, right? But rest assured, once the oxidation is complete, we will lower the temperature back down to ambient. So the inorganic salts, again, they will dissolve back into the water and they can get flushed out of the analyzer. So this video is basically a illustration of all the steps that I just explained of how the Innovox TOC analyzer oxidize the sample using the supercritical water oxidation technology. Right, so here's the sample coming in, it's getting heated up, pressure is increasing at the same time because it is expanding inside a confined reactor tube. Right, so your inorganic salts like your chlorides and your sulfates, you can see they're actually all at the bottom because they precipitate out, they don't get to interfere with the reaction anymore. Whereas your organics are easily oxidized to form the CO2, right? And then thereafter, this will go back to ambient condition and it gets flushed out. All this completed usually within about 8 to 10 minutes. So that is the time taken for one data point on the Innovox TOC analyzer. Okay, I come to the end of my slides. I will actually have 2 videos to share with you. So Krishna, it's okay to go to the video now?
Sure, Melvin. You can show the video first.
Okay. Hi, good afternoon. I'm here to introduce our Sievers M9 TOC analyzer. The M9 is the cornerstone of our TOC monitoring solutions, which we can offer to our customers. Right in front of me here is the portable configuration of the Sievers M9. And actually next to it, this is the online configuration which we actually brought back from a customer to do some servicing. Now coming back to the portable configuration, it uses a patented membrane conductometric detection technology which allows it to achieve unsurpassed accuracy even at extremely low TOC levels. The range of the M9 is from 0.03 ppb all the way up to 50 ppm. The M9 operates by measuring both the TC, total carbon, as well as the IC, inorganic carbon, of the sample. Thereafter, the inorganic carbon is subtracted from the TC, and that gives you the TOC value. Over here on the screen, this is a touch screen which we can configure how the analyzer runs. We are currently using it as a in grab mode. Alright, so we are running a grab sample. The grab sample will be introduced using a valve at the back of the analyzer where there is a sampler unit. So this is the sample handling unit with the valve and the sample inside. Right, it has a septum cap, and once you invert it and insert it inside the septum, inside the sampler, there is a needle inside the sampler handler which will puncture the septum cap and allow sample to be drawn into the analyzer. It is also possible to use this portable configuration for continuous measurement. So in some cases where customers may want to have an ad hoc measurement in the online process, or perhaps do some troubleshooting, they can actually have this portable configuration set up in their plant to tap at a certain point for continuous measurement. So the same sampler will be used, right? Just that instead of the valve port, we will close the valve port and we will have the tubings hooked up at the bottom to introduce the sample into the analyzer. Coming back to the main screen, right now we can see that we are setting up to run a grab sample. We can actually configure the analyzer to run on what we call the auto reagent mode, where it will automatically determine how much acid and oxidizer to use. You can switch this off and also manually change the values. The acid and oxidizer reagents which are required for this analyzer are actually in the cartridge form, and we can take a quick peek inside to show you where the cartridges are installed. There is also an option for this ICR, which stands for inorganic carbon removal. So for samples which have a large proportion of inorganic carbon compared to the organic carbon, it is recommended to use the ICR. It is also possible to set up the flushing time in case you are worried about carryover effect, and you can also set the number of repetitions you want to run per valve, as well as the rejects. So in some cases, again, because of carryover effects, you may want to reject the first or even the first two measurements. The analyzer takes only 2 minutes to measure one sample, and we even have a turbo option available where it allows the sample to be measured in 4 seconds. There will be some accuracy loss, but it is more intended for very critical applications where the customers need the data quickly to make process decisions. On the portable configuration of the Sivers M9, we also have a conductivity option which is now switched off, but this actually allows the analyzer to measure both the TOC as well as the conductivity of the sample. So both of these data will be available. At the back of the analyzer, there's actually a USB port which you can actually export the data once it's, the analysis is complete. Right, so I will just give you a quick look at one of the sample that I ran just a couple of minutes ago. So over here on the touch screen, you can select and look at the results in details. So I ran a 1 ppm standard solution. We have our own traceable standards, reference standards that we manufacture. So this is a 1 ppm KHP reference, and we ran this sample 4 repetitions, and you can see that we are actually achieving very close to 1 ppm and very low standard deviation as well. So these levels of accuracy and precision can be easily achieved with the Sivers M9 analyzer. Thank you for your attention to this brief introduction. If you have any further questions about the analyzer, please feel free to reach out to myself or to our local representative. I have one more video for the InnoVox. Hello, my name is Melvin and I'm here to give you an introduction of our Siever's InnoVox TOC analyzer. As you can see before me, this is the lab configuration of the InnoVox. We also have an online configuration available. Next to this particular setup, we have the auto sampler, which can be used to measure multiple samples. You can set up all the samples in the auto sampler and then get it to start so that it can run automatically. Over on the InnoVox right now, I am currently running one sample just to illustrate how the instrument operates. The analyzer uses a patented supercritical water oxidation technology to oxidize organics in the sample. Subsequently, the detection of the organics will be done using non-dispersive infrared. So we have an NDIR detector inside. The analyzer operates using two reagents as well as dilution water. So you can see these are hooked up on the side of the analyzer. We have an acid as well as an oxidizer, and the dilution water is there as well. We also require a carrier gas which is free of carbon dioxide for operating the TOC analyzer. But in this particular case, we have installed at the back of the analyzer, which you can see momentarily, this grey cylinder, which is air purifier. Inside is a cartridge which will scrub carbon dioxide away from the ambient air. The analyzer can operate using ambient air. So over on the front, we have the sample running right now. It is in the vial pot, as you can see. So samples that you want to run by grab sampling, you need to have this vial pot with the septum cap, and you will have to invert it and place it within this vial pot where there is a needle which will puncture the septum cap and allow the sample to be introduced into the analyzer. Here is our main screen, which is a touch screen, and you can use this to change the configuration of how you want to operate the analyzer. You can change, for example, the mode. So the analyzer operates in a number of different modes. First, we have the TOC mode, which you will have to measure two separate steps. One is the measurement of the total carbon, TC, followed by the measurement of the inorganic carbon, the IC, right? So you do a two-step measurement and then you will subtract the IC from the TC to give the TOC results. There is a faster way to operate the analyzer, which is using what we call the MPOC mode. It stands for non-purgeable organic carbon. Simply stating is trying to measure the organic carbon without accounting for anything that is volatile. So when we run the MPOC mode, it is a one-step measurement. Sample will go through a purging step first, where we will use the carbon dioxide free air to purge the sample, and thereafter it will go through the normal measurement step. The range on the InnoVox is from 50 ppb all the way up to 50,000 ppm, which is the highest range available in the market. And when we start the analysis, you can see on the screen here, it's in grab mode. There are a number of repetitions. So for one vial, you can set a certain number of repetitions. You can also set the analyzer to maybe disregard the first or second two readings because you may be concerned of certain carryover effects. So once you set up your sample, you hit the start button, it will show you for each of the repetition how much time is remaining, as well as for the entire vial, how much time is needed to process the entire vial. So over here, I've set up the sample to run just 3 repetitions. Once the analysis is stopped, I'll be able to show you more features on the InnoVox. In the meantime, regarding the measurement range, earlier on I did mention that it's from 50 ppb to 50,000 ppm. It is also possible to separate the range into 5 different ranges, so you don't have to calibrate this instrument throughout the entire range, right? You just select the range that is most relevant to the samples that you're running. So for example, if most of your samples are below 100 ppm, you can just choose to use that 0 to 100 ppm range, and you just calibrate that range. Okay. You can also set up different methods for the different samples that you're running. So for example, some samples may require less acid reagent or less oxidizer reagent, while some other samples may require more acid and more oxidizer reagent. So you can set it up and save it in the different methods. You can see at the bottom here of the analyzer there is actually a USB port. So any of the results that you get from your analysis can be extracted from here, either in the form of a PDF report or as a CSV raw data file. Right, so now the analysis is stopped. Right, I'm going to remove the valve. Okay, see this is the valve with the septum cap. So this is the valve port, which when you're not using, you should close it. Right, and at the side here we also have a sipper tube. This option for some customers who choose to sample from a larger bottle instead of through the valve. On the menu, okay, as I mentioned, it's touchscreen. You see that we are running now in grab mode. It's also possible to set up the analyzer to run in continuous mode if necessary. So if you have, let's say, a big bottle of sample at the side running through a sipper tube, you can set it up to run continuously to get a large number of data points. In terms of the calibration of the instrument, it can be calibrated only twice a year, so the stability is for 6 months. At the back, this is where the waste from the sample is coming out. So this is the amount of liquid waste that is generated. Typically there's not a large volume, so it's easy to handle. So this is a very brief introduction of our Sivers InnoVox TOC analyzer. If you have further questions, please contact our local representative, or you can reach out to me as well. Thank you for your attention. Yeah, thank you. So those were the videos introducing both the M9 and the InnoVox. That's all I have, Krishna. So back to you. Sorry for overrunning on my time.
It's okay. Very fruitful presentation from Melvin. Thank you very much for the the knowledge, Melvin. Anyway, however, the time is running out now, so I'm afraid that we only have time for answering only 1 or 2 questions coming from the attendees. Would you please see my chat on the chat room, Melvin? Bapak Ibu mohon maaf dikarenakan waktunya cukup mepet, jadi ini ada total cukup banyak pertanyaan yang masuk. Hanya di kesempatan kali ini kami akan menjawab 2 pertanyaan yang sekaligus kami juga nilai 2 pertanyaan ini adalah 2 pertanyaan yang terbaik, sehingga kami bisa sampaikan bahwa pertanyaan dari Bapak Rian Cendiriawan dan kemudian kedua itu ada dari Bapak Nafian Awaludin. Jadi untuk kedua nama yang tadi kami sebutkan, nanti tim dari Tawada akan menghubungi secara private untuk melakukan mungkin komunikasi mengenai pengiriman dari gift yang kami sebutkan tadi di awal. Okay, Melvin,
Yeah.
you can start answering the question. Only 2 questions, I'm afraid.
Actually, okay, first I'll try to answer the questions as many as I can. Actually, I don't mind staying on the line a bit longer if the audience is fine with that. So first one, I think is about the pre-treatment required to check for seawater RO, right? For seawater because of the high chlorine.
Sorry, Melvin, before that, the one coming from Parian, what are the key factors that affect? You can see the Q&A.
Right. Yeah, I saw that
Yeah.
question. So, okay. So, key factors affecting accuracy and reliability. I think we need to understand, first of all, what are the levels of TOC that you want to monitor the water quality. Over here, you're talking about boilers. So it's, in terms of utility water, which is, in our opinion, relatively clean. When you're monitoring this on the, let's say, for example, the Sievers M9, chances are that you actually get a very stable reading right off the bat. So there are very little things that will actually affect or cause interference to the TOC measurement because, like I said, with our membrane technology in the M9, we are very specific to just the CO2. We are isolating the CO2 for measurement, and this CO2 is coming from the oxidation of the organics. So we don't get interference, unlike, other parameters or other brands of TOC analyzers. I hope this answers the question.
Okay. Thank you. And the next one is from Pak Nafian Awaludin, the SWRO.
Seawater RO, right? Okay.
Yes.
So yes, Pak Nafian is right to say that chlorine definitely or chloride does cause interference with the TOC analysis. Chloride is what we call an oxidizer scavenger because it reacts preferentially with the oxidizer reagent that we add for TOC analysis. So this is basically where the InnoVox comes in because the technology of the InnoVox is a supercritical water oxidation approach is the one that you want to use to overcome this chloride interference. When you push the sample to this supercritical condition, the chloride so-called falls out of solution and it doesn't interfere anymore. So you get this environment where you are able to oxidize just the organics alone easily. So definitely I would recommend the use of InnoVox when you are talking about samples that have a high salt, right? So it's not just necessarily seawater alone, but even something like brine, we are able to analyze that on the InnoVox analyzer.
Okay, so next one coming from Budian Palastro. What are the benefits using TOC analyzer compared with conductivity TDS in food manufacturing? How about the investment between those two methods?
Right. So I'll be very candid here. I think, of course, conductivity is probes are much cheaper compared to a actual TOC analyzer, but then the benefits are different as well. So it depends on where you want to use these tools, right? So sometimes we have customers using them for, say, for example, source water monitoring. Again, you're trying to achieve different things, right? With TDS conductivity measurement, you're looking at inorganic contamination. But with TOC, you're looking at organic contamination. Which of this is more important to you, or which will actually have a bigger impact on your process? That is really the question that you need to answer. So perhaps you are monitoring the source water just before it hits your RO membrane. In which case, maybe you might be more concerned about organic fouling of your membranes. In which then, conductivity doesn't really help you there because you don't really see the organic compounds with conductivity or TDS. You need to actually use a TOC to see the organic compounds. A very interesting application in food manufacturing that I've come across is actually what we call cleaning verification, because in food and beverage manufacturing, most of the time it's a batch process, right? And in between batches, you want to prevent cross-contamination. So many of the tanks and the vessels that are used for F&B manufacturing, they need to be cleaned in between batches, or even sometimes when you do a product switch over. So there's this so-called clean in place step, or CIP, and some of the customers implement TOC analysis at the final rinse step of the CIP. So during the CIP final rinse, when they are cleaning it with so-called the cleanest water available in the plant, they will actually monitor the TOC coming out of the vessel to see whether it's really clean, because sometimes you don't want to open up the vessel to do a so-called like an invasive check. So just by looking at the TOC value of the rinse water, they can actually determine whether there's any residue, either of the product or even the detergent that's left inside the vessel.
Okay, so I'm afraid this one will be the last question you can answer, Alvin. So it's coming from Ibu Yonada Hairunisa. So the question is actually, is TOC analyzers can be used for the production area in food industry? Since in this area, normally the one that analyzed is the organic one. So, and also is there any risk from carbon organic itself?
Okay, so I think in the production area, the application that I just talked about is really relevant, the cleaning verification, where you're trying to prevent cross-contamination between batches or when you do a product switch over. Sometimes you are concerned about, the flavor carryover because F&B plants typically they don't just manufacture one product, they manufacture a number of different products and they use the same process equipment. So you don't really want the flavors, say for example, your coffee flavor to carry over into maybe a green tea that you're manufacturing. So a lot of these flavor compounds, even the ingredients that you use for F&B manufacturing, if you think about it, these are all organics, right? Carbohydrates, proteins, sugars, they are all organics. So then TOC becomes very relevant because you're trying to check for trace amount of these organics after the cleaning process. So that's really where the TOC can be implemented in the production area, I think.
Okay, thank you. Melvin, I'm afraid that we are running out the time, so we have to end the webinar itself. So thank you again for answering the questions. I already take note of what is the questions, the complete questions, and then we will answer it by email or direct phone call to the customers. How about that, Melvin?
Sure, that works out for
Sure.
me.
Okay.
Thank you again. Thanks again to
Okay.
the audience for their attention.
Oke, thank you. Bapak, Ibu, dan rekan sekalian, dikarenakan saat ini malah sudah lebih dari 1 jam dari waktu yang direncanakan, kami mohon maaf. Jadi, maka dengan berat hati kami harus akhiri sesi webinar. Di kesempatan kali ini, perkenankan saya selaku moderator untuk sekali lagi mengucapkan banyak terima kasih dan juga kami mohon maaf bila pada sesi webinar ini ada penyampaian atau hal yang kurang berkenan di hadapan Bapak, Ibu, dan rekan sekalian. Mudah-mudahan kita dapat bertemu lagi di lain kesempatan. Atas kesempatan dan waktunya kami ucapkan terima kasih. Kami mohon pamit. Akhir kata dari Tawada dan juga dari Veolia mengucapkan banyak terima kasih sekali lagi. Selamat siang dan wassalamualaikum warahmatullahi wabarakatuh. Terima kasih Bapak Ibu. Pamit.